Hey, what's up guys? It's Nicola from Calcunic, and today we're going to be talking about proof by mathematical induction. Let's get right into it. If you've studied any higher level mathematics, you'll notice that the proof by induction comes up quite often, and so it's an important tool to know and learn. First, we'll start off by defining induction. So say we have this statement, call it P, and we say that it depends on n, where n is a natural number. So if we could show that statements 1 and 2 are true, where 1 is that P of 1 is true, so just that it's true for n equals 1. And if we could show that for all k, where k is a natural number, if P of k is true, then P of k plus 1 is true, then we have proven that for all n, where n is a natural number, P of n is true. So apart from the definition, this is how we actually go about using induction in our mathematical proofs. It's a two-step method, and first we want to show our base case and next the inductive step. So what's the base case? Well, the base case is just establishing that it's true for the first element in the set that you're trying to prove under. So if we're trying to prove for natural numbers, our goal is to prove that P of 1 is true because 1 is the first natural number. And the way we do that is just to substitute n equals 1 into the equation we're trying to prove. Now we go on to the inductive step, which is split into two parts, the inductive hypothesis and also the inductive conclusion. So first we assume P of k is true and k is just any arbitrary natural number. Our goal is to use that assumption, the inductive hypothesis, and to prove that P of k plus 1 is true. And this is what we call our inductive conclusion. Once we've shown the base case and the inductive step, we could go on to finish our proof and write a concluding statement and nicely write that the result holds for all n greater than or equal to 1 by the principle of mathematical induction, or just POMI for short. Now, although induction doesn't have a lot of steps to it, a lot of people still struggle with how to implement it into their proofs. And the main reason for that is because they don't actually understand the logic as to why induction works. Personally, I think the best way to understand it is to look at the domino analogy. So let's just draw a few down right now. And so as we've seen with induction, we know that we have a base case and an inductive step. So we could look at the first domino as the base case and say we're just going to draw an infinite series of dominoes. Now, if we consider what's actually being proven with induction, it's just the base case and the inductive step. And so what we're saying in the base case is just that P of 1 is true, and in the inductive step we're saying that if P of k is true, where k again is just any arbitrary natural number, that P of k plus 1 will also be true. So let's now try to incorporate these two steps into our analogy. We look at the first domino as the base case. Once we've shown that the statement holds for n equals 1, we could think of that as showing that the first domino will fall and hit the second one. Now, the inductive step is showing that if we pick any arbitrary k, we know that k plus 1 is true. Well, taking that into domino perspective, we could say that if any one of these dominoes is falling, it will hit the next one and make that one fall as well. So look, from the base case, we know the first one is falling and hitting the second one. So the second one will be falling, and by the inductive step, it will hit the third one. And then the third one will hit the fourth one, and so on and so on and so on. And so we see that with this recursive logic, every single one of the dominoes will fall. And taking this back into terms of the induction, it will mean that by just proving the base case and the inductive step, we've shown that the statement holds for all natural numbers. Okay, so we're going to start off with a slightly easier problem to ease our way into proof by induction. So we have that we want to prove that 6n minus 1 is always divisible by 5 for any n, where n is a natural number. So as explained before, we start off with our base case. Base case. And we have that our base case is when n equals 1. So let's just input n equals 1 into the equation. We get that 6 to the power of 1 minus 1 is equal to 5. And hopefully we can all see that 5 is in fact divisible by 5. And this line in the middle just signifies divisibility, so not to get confused with that. 5 is divisible by 5. So we've proved that. We can write a quick check mark on the side to remember that. And now we go on to the harder part, the inductive step. And so as explained before, we start off with saying that we pick k, where k is just an arbitrary natural number. We assume that 5 is divisible by 6k minus 1. And how we got there is just replace replace the n here with k. And now our goal is to prove that 5 is divisible by 6k plus 1 minus 1 using this assumption here, which is the inductive hypothesis, and this here is our inductive conclusion. So let's go on now to prove this. We're going to start this proof off by writing 6k plus 1 minus 1. And note that this is just equal to 6k plus 1 minus 6 plus 5. Note how here we have minus 1 and here we have minus 6 plus 5, and so they're logically equivalent. I just added 5 and subtracted 5 at the same time. And you'll find out why in a second here. And so we're going to factor out the 6. So we're going to have 6 times 6 to the k, because we factored out a 6, minus 1 plus 5. Now if we look at what we have here, we could split this up into two components, this one and this one. And so if we look at just 5 here, we know that 5 is divisible by 5, obviously. And we have here, we already know that 6k minus 1 is divisible by 5 by the inductive hypothesis, and so therefore 5 is also divisible by 6 times 6k minus 1. And so since we've shown that 5 is divisible by this and also this, and we're simply just adding these two terms, we can conclude 5 is in fact divisible by all of this together, and all of this is just what we have right here. So we have that 5 is divisible by 6k plus 1 minus 1, proving the inductive conclusion. And then we finished our proof now, and we could just quickly write, therefore 6n minus 1 is divisible by 5 for all n element of the natural numbers, and sorry, this upside down a just means for all, by the principle of mathematical induction. And there you have it. We finished our first induction problem. So let's go on to our next question now. It reads, prove that for all n where n is a natural number, show that the sum from 1 to n is equal to n times n plus 1 over 2. And if you don't understand this notation, it's just called sigma notation, and basically what it means is we're doing 1 plus 2 plus 3 plus all the way out to n. It's just a nicer way to write it, more concise. And so like before, we start off with our base case. And the base case is when n equals 1. And so we know that the sum from, let's write it out, the sum from I equals 1 to 1 is just equal to 1. And if we input 1 into the equation, 1 plus 1 over 2, this is just 1 times 2 over 2, and hopefully you all know that this is just 1. We have 1 equals 1, that's great, the base case holds, and we could write ourselves a quick check mark on the side so we don't forget it. Moving on, we go to the inductive step. And like always, we're going to write, we pick an arbitrary k, where k is a natural number, and we're going to assume that the sum from I equals 1 to k is equal to k times k plus 1 over 2, and we wish to prove our inductive conclusion, which is that the sum from k plus 1, from I equals 1 to k plus 1 is equal to k plus 1 times k plus 2 over 2. And how I wrote these out, if you have any confusion, for the inductive hypothesis, we just replace every occurrence of n here with k. And in the inductive conclusion, we just replace every occurrence of k here with k plus 1. You'll see, so we have k here, k plus 1, k plus 1, and k plus 1, and that's k plus 2 there. So let's go ahead and start proving that. I usually like to start these with summation. I start with the left-hand side of the inductive conclusion and work my way to the right-hand side. See how to do that. So let's get started. We have that the sum from I equals 1 to k plus 1 is equal to, and if we look at what I wrote before right here, we could, this just means 1 plus 2 plus 3 plus 4 all the way to k plus 1. So we can actually separate this into two components. We could separate it into k plus 1, and we could also separate it into another summation. This one goes from I equals 1 to k. And you'll notice that these are the same. I'm just separating it, and you'll see why in just a second here. And what I'm going to do is I'm going to take this and replace it with what we have in the inductive hypothesis, okay? So we're going to get that this is equal to k plus 1 as before, plus k times k plus 1 over 2. Now we do some quick math. We're just going to factor out the k plus 1s. Here we have 1 from before and plus k over 2. And if we find a common denominator, we could get that this is equal to k plus 1 times k plus 2 over 2. And if you look at that, we have just proven the inductive conclusion. We have right here and here is just this. So we have indeed proved the inductive conclusion. Give ourselves a quick check mark. And now we can just write, therefore, for all n, where n is a natural number, we have that the sum from I equals 1 to n is equal to n times n plus 1 over 2 by the principle of mathematical induction. So let's go ahead and start our last problem. It reads that we let a of 0 equals 0 and a n plus 1 equals root 2an plus 5 for all n greater than or equal to 0. And our goal is to prove that 0 is less than a of n and is less than or equal to 4. Now that we've seen a few examples, I'd recommend pausing the video and trying the problem on your own before continuing and watching the explanation. So, as we've always done, we start off with our base case. And this problem is unique in the way that our base case will actually be n equals 0, not n equals 1. And I know that we've had n equals 1 as our base case for the last two examples, but if you look at the logic behind induction, all it really needs is just a base case and the inductive step, and that's enough to prove. It doesn't matter if you're starting at 1, 2, 3, or even any number. Just as long as you have a base and then your inductive step, you can prove it for that set of numbers. We're just using 0 because in this problem we have that it starts at a0, so that's going to be our base. So let's verify if the base case holds. So we have a0 equals 0, and well, in fact 0 is less than 0, less than or equal to 4. So we've proven that. We could give ourselves a quick check mark. Now we go on to the inductive step. So the inductive step, and once again, as usual, this doesn't change. We pick an arbitrary k, where k is a natural number. And we're going to assume 0 is less than or equal to ak, less than or equal to 4. And that's our inductive hypothesis. We wish to prove that 0 is less than or equal to ak plus 1. Less than or equal to just 4. Okay, so the way I usually go about approaching these problems when we have a constraint with less than or greater than, I usually start off with the inductive hypothesis and try to move our way to make it look like the inductive conclusion somehow. So let's start with that. We're going to start off by writing 0 is less than or equal to ak, less than or equal to 4, right? And so what we're going to do is we're actually going to try to move and multiply and add some things to ak to make it resemble this. Because once we've done that, we could replace this with this because they're equivalent from the definition of the question. So what I'm going to do is multiply ak by 2 and add 5. And if you don't understand that right away, it's fine. You'll see just in a second why we're doing this. So we do this to all sides. So we have 0 times 2 plus 5 is 5. have here 2ak plus 5, and 2 times 4 plus 5 is 13. And now we're going to take the square root of everything. So we have here root 5 is less than 2ak plus 5, and the square root there, less than or equal to 13. Now we can notice that this is literally just ak plus 1 from the definition of the question. So we're going to replace what we have here with that. So we can write root 5 is less than or equal to ak plus 1, less than or equal to root 13. Sorry, I missed a root here. And in fact, we know that 0 is less than this, and root 13 is in between 3 and 4, so this is less than or equal to 4. And then we could conclude that 0 is less than or equal to ak plus 1, less than or equal to 4, which is just our inductive hypothesis. So we've proven that. We can write our concluding statement now. Therefore, if we have that a0 is equal to 0 and an plus 1 is equal to 2an plus 5 and the square root of that, then 0 is always less than or equal to an, and an is always less than or equal to 4 by the principle of mathematical induction. Alright guys, thanks for watching. If you had any questions or suggestions, please leave a comment. I'd be happy to get to it. And if you enjoyed today's video, or if you feel like you learned something, please do leave a like and a subscribe. It would really help me grow my channel. That's all from me. Until next time.